4. Okay. So at the bottom, so QZ. So I'm going to take the major wet first, 2, with his 0.5. Depth is 4.79054, right? And then Y bar is equal to 4.79054. And then we divide by 2 again, right? Then we are going to plus the width is 10. The depth is 0.5. The Y bar is 4. No, the Y, not the no, the width, the depth, the Y bar now. So it's 4.79054 minus by 0.5. Oh no, minus by 2, minus by 0.5 divided by 2. Okay, so this will be equal to 4.79054 squared divided by 2 times by 0.5 times by 2 is equal to 11.4746. Okay, and then plus, let me do it again, 2 times also 0.5. 11.4746. So 4.79054 minus 2 minus 0.5 divided by 2 times by 0.5 times by 10 is equal to 12.7027. Let me do it again. 79054 minus by 2 minus by 0.5 divided by 2 times by 0.5 times by 10, 12.70. So this will be equal to 11.4746 plus by 12.7027 is equal to 24.1773 inches to cube. Okay, so either you take from top or take from bottom, the answer will be the same. Okay, so the shear max is equal to V over I. Okay, we have calculate Q max, and then we have to divide by 2 multiplied by the thickness. The 2 is because of box beam. You have Q on the left hand side, Q on the right hand side, so it's a box beam configuration. So V 5,000. I remember I is equal to 145.98. To thickness 24.1773. Okay. So this will be equal to 5,000 times by 24.1773 or 5.98 divided by 2 divided by 0.5. So the wait, one wait 5,000 times 24.1773 divided by 5.98 divided by 2 divided by 0.5 is equal to 82. I get 82. 5,000 times by 24.1773 divided by 145.98 divided by 2 divided by 0.5. Yep, 828. 828.103 psi. Or if you want to calculate Q max, then it'll be equal to 5,000 multiplied by 24.1773 divide by 145.98 and then you just divide by 2. Okay, so 5,000 times 24.1773 divided by 145.98 divided by 2 is equal to 414.052 pounds per inch. Okay. So again, I did not prep this question. Okay, I'm just doing it. Okay, and I like you to have that confidence. Okay, the confidence in the sense that whether you take from the top or from the bottom does not really matter. The answer will be the same. Okay, so this is thin wall analysis. Okay, there is an example in the homework. Okay, let me drop the homework. And why I did this example, because it will help you in your homework, the latest one. Yep, I found it. So, right. So it's not exactly the same, right? But it's similar, right? So if you look at this question, right, which is from the homework, they ask you to find stresses at point A and point B, right? But this example is easier because the structure is symmetry about the z-axis. Okay, the top and the bottom are the same. So if we were to sketch this out, if I were to sketch this out, and we only need to sketch half of it, right? This is one part, and then you go another piece. And then I'm going to put a green line, which represents our geometric centroid, right? So I only sketch half of it. And we know that over here, right, this is point A. And over here, this is point where? Point B, right? So the major web, as you can see, these are all your major web. Construct your shear flow. Right? And then you know that this is your terminal. Right? This is your terminal 1. And then over here, whether you design going out or coming in does not matter. You know that this is your terminal what? Terminal 2. Right? So you have two terminals over here. And then you know from A, right? You pick the closest terminal and the direction is the same, right? This is the first moment of area from point A. Okay. But when you look at point B, which is over here, right? Does it start from terminal 1 or terminal 2? So based on the same concept that we have come from the previous example, we know that it's going to be from where? Terminal 2. Okay. Now, if we have another point, and this point is placed over here, this is our point D. Okay, so we have our point B over here. And then we have our point D. If point D, if that's the case, then you have to take this area over here together with this area. Okay. And together with this area. Why that's the case? Because at point D, the shear flow direction, the arrow is from vertical. If it's vertical, the original is from where? From T1. Are we clear? Okay. So this has to be crystal clear to all of you. So what if now I have another one over here, and this is our point E? If it's for point E, then we have to take the entire, I'm going to draw a red line. We have to consider the entire what? Shear flow, the top. Are we clear? Okay. So that is how you have to make a decision on where to choose your first moment of area. Okay. The next example that I want to do is one of the most difficult question in this thin wall analysis. Okay, so as I said, is the most difficult. Okay, because you have to know how to apply the rules. Okay, very well. Okay. Again, another thing I want to emphasize is we are going to, this is the fundamental. Okay. It has to obey this fundamental rule. Okay, you cannot break this rule over here. I'm going to, okay. So a plate 2 millimeters is bent as shown, and then used as a beam for a vertical shear of 5 kilonewton. Determine the shearing stress at the first 5 points indicated and sketch the shear flow in its flexion. Okay. Okay, so we are going to sketch the shear flow. So again, I'm not going to waste time looking for first moment of second moment of area. You know how to do that. Okay. So I'm just going to write down our I. So I'm going to do our transformation first. Okay. Let me expand this. Okay. So our I, so this is our Y, this is our Z, this is our rotation bar X. Okay. So our I, ZZ, will be equal to 133.76 times 10 to the power minus 9 meter whole. Okay. So the next thing we do, we are going to construct our shear flow. Okay. Again, we have to identify the major web. Major web control the flow. So this is we're taking Vy coming from the top. So we know over here, this is our terminal number 1. Terminal number 2, terminal number 3. Okay. Initially, it looks really complex, but your design is not that bad. Okay. So you draw, you put down your geometric centroid. Okay, so the geometric center is somewhere, not somewhere, it's over there. Okay. So the first thing that we're going to do